So far, so last time we talked about the response of a single degree of freedom system under harmonic loading. So that means if we have a spring, mass, and damper system there, and if that system is under a harmonic loading, such as we have that equal to 0 times sine omega RT and omega RT. So the response of the mass system, for example, the displacement of the mass can be expressed in terms of the natural frequency of the system as well as the frequency of the force. So so basically, if you are so here, and I use the system. So here, actually, using MATLAB, we can simulate the response of a so on the right side, there is a monitor. So that monitor is used to monitor, and I have already created a spring, mass, and the damper here. The spring and mass over here. So this system can use the monitor to monitor the displacement of the mass. So basically, if we can take a look at the mass property over here, the mass property. So for example, the mass of this system is equal to 1 kilogram. And we have the spring system over here. So the spring is also equal to 1 Newton per meter. So what's the natural frequency of the system? So the system here, we have M equal to 1 kilogram, K equal to 1 Newton meter. So the natural frequency of this system should be equal to 1 K over M equal to 1 over 1 equal to 1 radius per second. That's the natural frequency of this system. So here we just will assume the C equal to 0. So it's undamped system. So basically, the response of the system, the UT time, is a function of the natural frequency of the force here. So if we, so the sine wave will give us the input. The input is the sine wave. So for example, here we have the amplitude of the force equal to 1. So remember all the force, the mass, and the spring constant is also all equal to 1. So we can do a quick check to see what will happen. So for example, if the frequency of the force is very small, 0.01, so the natural frequency of the system is 1. So this is much smaller. So we can do a quick check. We run the simulation. as the response of the system is given. So as you can see here, the vibration of the system is with a very large area, with a very small frequency here, and the maximum displacement for the mass system is equal to 1, so the force equal to 1, k equal to 1, so the rate displacement is equal to 1. So the analysis of the system when the frequency of the force is very much smaller than the natural frequency. Basically, the analysis is pretty much like a static analysis. You can compare the maximum displacement is equal to the static displacement. So this is what we discussed the last time. And also we can take a look at, for example, if we have a frequency equal to 0.9, what will happen over here? When the frequency of the force is very close to the natural frequency, but not equal to natural frequency, what will happen? Really? Yeah, we should check that his nose. Yeah, the nose is correct. We will have beating. So let's say what will happen here from the analysis. Oh, probably we'd better to. So this is beating. Right? If the
Change.
I change the frequency of the force. So the frequency of the force is equal to 0.9, and the natural frequency of the system equal to 1. They're very close to each other, but not equal. So we will have beating. So this is beating. And we can also use 1.1. So another also close to run the analysis. Beating again, because the frequency of the force is a little bit larger than the natural frequency, not equal. So this is beating. So how about 1 equal to 1? If the natural frequency, if the frequency of the force equal to 1, what will happen? Equal to 1, what will happen here? In resonance. This is called resonance. So with time going, the amplitude increasing. This is resonance. And another case we have already talked about is if we have the frequency much larger than the natural frequency, for example, is 100. What happened here? That's where the motion stops. So if the frequency of the force is much larger than the natural frequency, you will see the motion starts. Yes,
Could you do something like 20 to see like how it
okay,
actually gets large?
sure. So we can adjust. We can adjust in the way. So for 20, the maximum is very small. It's 0.04. It's sine wave. But the amplitude is much smaller than regular frequency threshold. So so for all the cases, we have already seen some similarity here. So like because we input a sine wave. So here, this is the input. This is the system. So the system, we have the input. Force is a sine wave. So the output is a sine wave. Right? So if you input a sine wave to the system, we will get the sine wave for the system. But in the real world, there are a lot of different types of waves, such as besides sine waves, such as, so for example, if we have in summary, we know that for harmonic loading, if the force is a sine wave or cosine wave, that's the same, basically. The displacement pretty much so a sine wave. That's what we have already observed. The response of the system under a harmonic loading. But if we have a different case, how about a rectangular? Node. I don't know what G is that displacement. So if here we have the PT is not a sine wave anymore. And this is a PT and this is T, right? For example, this is a T0 and this is 1 second. So for the first second, we have the force equal to a constant number. If the time is other than 1 minute, we remove that force. So what will be the shape of the displacement? Will it be a rectangular? Triangular?
Triangular.
Are you just guessing?
Trying to throw in like a moment, shear force to moment. Up the same.
Oh. Taylor says a circle.
Way off.
Circle? Well, very creative. Right? Circular? So what will be the shape of the displacement? So online students, what are your thoughts? What will be the response?
I'll Perry to wake up.
So Perry, Anthony,
Everyone will pick up.
wanted to check if you're still awake. guys hear me?
Oh.
Yeah, you hear us?
Oh, yeah, something wrong with the speaker. Your voice is too low to hear. So yes, so online students, please make your suggestions through the chat window. So what will be the shape of the, or anything else?
You're crazy.
The bonus point, if some of you can figure out the shape of bonus point.
Parabola.
One bonus point.
Uniform.
That's good.
Uniform? Okay.
Uniform.
Are you guys now just yelling out
That's when
shape?
they push down for 15
You get a bonus point. Parabola.
Okay. All right. So the list is getting longer and longer. So
Sticking with my try.
any additional input? If no any additional input, we will do the test.
Start.
I put on try.
For linear.
Try.
Okay, let's see who will win the bonus point.
Oh my god.
So,
That was my next.
so here,
It's Patrick. It's Patrick.
so here, yeah, I did the same model, but here, the input is not a sine wave. The input is from an Excel file. So basically,
Comes out still sine wave.
I have already created several here. Okay, here it is. Here in the screen. So here, now the input is not a sine wave, so I have to make some
They really do.
unique ones. So for example, in this case, this is a rectangular shape, right? So 0 to 1, the force is equal to 1. From 1 to 10, the force is 0. Okay. If the time is under than 1, the force is to 0. So that's a rectangular shape. That's a rectangular impulse. So what will be the result here? Let's see. We change the input. So the input is from the file called earthquake record. So the name is called rectangular, right? You know. You guys ready? It's the mass is the same, the spring, the same, the
Now there's a
damping ratio, let's just use the damping ratio equal to 0.
Wait, I want to add one more.
And one more, okay,
Exponential.
okay, exponential.
fractoid.
What?
That exclamation point,
Oh, factorial.
factorial.
It doesn't
Okay,
exist.
factorial,
Plot
okay.
twist.
Anyway, let's
Yeah.
see.
Probably glitch.
Are you guys ready?
I am
Yes.
ready. Let's do it.
Let's just run it, right?
Oh, Rick.
Oh,
Yes,
Yeah,
I got it. You're right.
oh, rectangular, probably some, rectangle, sorry. My fault. But then rectangle under the rectangular. Oh,
There's no E.
There's no U.
tangle.
I already do it. I have to write it down. Kelly.
Well, we just need the first 20 minutes, 20 seconds. So,
So.
you guys are excited?
It's a sine wave.
It's a,
Yes, it is.
Unfortunately, nobody gets
To me.
all the points. It's a sine wave again.
I knew it, it was a plus.
so is the displacement always a sine wave?
Not
clarify
always,
this.
not always. Not always a sine wave.
Is it a cosine wave?
Not always. We'll see.
It's all basically a wave.
Oh, it's like.
Okay, basically, even we have a rectangular input over here, the response, the displacement will be a sine wave, other than the mist that you have already put up together. So yeah, no, unfortunately, so hopefully next time, the ball is going here. So now let's talk about the new topic tonight. So that's the response of the single degree of freedom system under arbitrary load. Any shape under the sine or cosine wave.
Yeah, on camera.
So this is a topic tonight. So response. Under arbitrary mode. Any types of load should be with. So the objectives for tonight. Right. Impulse. Calculate. Under the. So basically the second objective is based on the result of the first objective. The first thing we need to know what is the impulse. No. The impulse node is node. Very short duration. Okay. Why impulse? Graphically, and we should be able to show the typical pulse load. See the force, or So this is a typical impulse node. Very short time it reaches the maximum. Then you may force may change its direction. So basically, there are two phases. So the phase one from 0 to the time where the impulse node becomes 0. So this is phase 1. And after that, this is phase 2. So phase 1, typically, let's say, forced behavior. This 2, that's spring vibration. So from 0 to T, the T1, the response of the system is a function of the force. While after T1, the system will do free vibration. So that with initial vision, T1, the displacement and velocity determined E equal to T1, T equal to T1. That's the definition of impulse. So that's different from the harmonic load. Harmonic load, we have the sine wave 0 time equal to 0 to forever. Here, we have the duration of the force is limited, very short time.
Something hits something.
Oh, yes, correct. So for example, the impact loading. If a car hits the column of a bridge, right? Or you have a bullet hits the bulletproof vest up there. Or you have a blast loading is also a good example here. For example, blast loading. Explosion of explosives use the plastic loading. The plastic loading is because in a very short duration, which is its peak load. So that's the main reason why we need to investigate the response of the system under this type of load. Design for plastic loading is also important topic for structural dynamics. So now let's start from the easiest case. The case for blast loading may be more complex here. So now let's say the easiest case. What's the easiest case? Rectangular. We have a rectangular load here. Response. Rectangular. It's a time. So basically, we should be able to write down the time function of the force. what will be the function? The form of the function in this case, right? So when time equal to a time smaller than t1, larger than 0, force is equal to p0. And then when time is larger than t1, force is equal to unequal to 0. Equal to 0. So this is the external force. And firstly, we consider a undamped system. And the fixed one. So for the undamped system, the fixed one, where to start? We start from the equation of motion, right? So the equation of motion is the equation of motion. Right? So any questions? To here. And the inertial force plus the spring force equal to external. So that takes, in order to figure out the response of the displacement, we need to solve this differential equation. So similar to the case where we have the harmonic load, the solution of this equation is parts. The general parts, we have the UC to A times psi helps. We got NT plus E. Well, we have a special particular solution. What will be the particular solution in this case? The particular solution could be P0 over K. So by inspection, we should be able to tell particular solution should be P0 over K. So that's a static displacement. Any questions up to here?
Example of a rectangular force.
Do you want to have an example?
I get like something hitting something for the last one, but what
Okay.
is a rectangle?
So for example, for a rectangular force, so the weight of this remote control
Okay.
is a constant number, right? So so this is a time 0. I put it on the top of the table, and then I remove. Right?
Yeah.
So that's a rectangular. Right? So initially, you have a weight of the remote console added to the top of the platform and remove it. So that so theoretically there are some vibration of this system over here, but since the platform is very deep and very tiny bags out there, so you will not see any vibration by lake ice. But if you use some very sensitive sensors, probably you can get the data of the vibration. Vibration is anywhere. So actually, in structural design, a lot of load is treated as static load, but actually, all the loads are dynamic load. Anytime when you apply a force, there are some vibration in the initial stage before the structure is stabilized. I mean, initial vibration. So does that answer your question? Yeah. So so that then we should be able to write down the full solution here. So that's equal to full solution here. So now we need to consider the initial condition. We just assume the system does not have any initial displacement or velocity, such as the platform. Assume the initial displacement equal to 0. The initial velocity is also equal to 0. So that we should be able to solve. Minus A. Is the velocity. So taking the initial displacement. Equations of 0 should be equal to minus E0 over K. So the UT this is the initial, the phase one, the forced vibration, the forced vibration. Does this make sense? We took a look at our actually the initial part is not the sine wave. It's not a sine wave. So this duration is 1 second. We just move that to here. From 0 to 1 second, this part is not a sine wave. It's not a sine wave. But very close to the sine wave. It's the form of this. So if we plot this equation in the space of time, right? can have the this is the displacement, and this is the time. Something. Something like this. But it's also a function of the frequency of the system. T equal to T1, yeah. Calculate the displacement. See the forced vibration, of course. The natural frequency is, for example, if we change the natural frequency of the system here to change the mass to 4. We have this. So it's a function of the natural frequency itself too. So some important thing here is what is the static deformation if we have a force here? So if we have a force equal to P0, what is the static deformation of the spring? The static deformation should be equal to the amplitude of the force over the spring, constant. But what is the maximum of the displacement for dynamic case? What is the amplitude of the, what is the maximum displacement? 2 times P0 over K. So that means if you have a constant force applied to a structure, if we consider that dynamic loading, the maximum displacement should be 2 times the force over the spring. So yeah, so that means in some cases, if you have dynamic loading, you have to amplify the load that is applied to the structure to calculate the real response. The maximum 2 times static. And that's the phase 1. That's a forced vibration. So any questions after here? So now let's say what will happen if we take a look at the phase 2. Phase 2, the equation of motion is different for phase 2. For the phase 2, the load is removed. External equal to 0. So we have, you can define tau equal to E minus T1. And we can so for the phase 2, it's a free vibration. So the initial stage or the initial condition is is when T equal to T1. But here we wanted to introduce another time, the time tau. So that's the time counted starting from T1. So we should be able to write down the free vibration. Free vibration. And we have already know the free vibration equation. So the U tau, that's equal to A times sine omega n tau. So this is equal to that's what we have already figured out. Right? So the free vibration at the time tau should be equal to the initial velocity over omega times sine tau, where the plus the initial displacement. Displacement time. So now we can write down the time, the UT. Right? Should be equal to U. So this is the phase 2. Phase 2, that's a free vibration. Cosine. basically, we should be able to plot two. Up to now, we should be able to plot the response of the displacement for the whole E. One. And here equal to square root. This one here, 2 times. So for the two stages, for the two phases, we have different amplitudes and amplitude. So that's where we have a rectangular response. That's the response. A rectangular, parabola, circular, on and on. But very close to sine and cosine waves. So any questions up to here? Okay, if not any questions, let's have a short break and resume the class. It's 8:40, since we started a little late, and let's have a little bit shorter break than later. Thank you.